This is chapter 4. This lecture is about chapter 4, which is Fourier series representation of continuous periodic signals. The outline of the lecture presentation is we'll discuss what is Fourier theory, why it is important, and we'll discuss about eigenfunctions and their properties, complex exponentials as eigenfunctions of linear time invariant systems, Fourier series representation of continuous time periodic signals, convergence of Fourier series, properties of Fourier series and linear time invariant systems, and examples of continuous time filters described by differential equations and filtering. Okay, to start with, we can start with the question, why is the Fourier theory important? Actually, the Fourier analysis is the transformation of a signal from time domain into a frequency domain. So that means looking the signal from frequency domain perspective. Okay, you can look any signal from time domain perspective or from frequency domain perspective. And a Fourier transform is a transformation of a signal from time domain to frequency domain. So why we go to frequency domain? In some cases, it is easy to understand and to interpret signals in the frequency domain compared to the time domain. That means you can easily, for example, recognize the frequency content of a signal more easily in frequency domain compared to time domain. For example, if you have this continuous time domain signal, it's difficult to see what frequency contents it has from time domain perspective. But if we change this to frequency domain, you see it has spikes here and here. It has two frequency components. So this we can see it easily. That means this signal. And after looking signals in frequency domain, the second very important thing is it's possible to design systems, for example, filters that filter out high or low frequency components of the signal. So if you'd like to remove the high frequency content, for example, of the signal, first you need to observe it in the frequency domain. So you have to decide which frequency part you are going to remove, either the low frequency, the high frequency, or somewhere in between. And filters are very important elements of many electronics and communication devices. For example, radio systems, television systems, mobile phones, all these, they have filters. So that is another very important another important advantage of the Fourier theory. Now, for example, if you see this signal, it's a noisy signal. This noisy signal, you can filter it. Noise is added to the original signal. You can filter the signal to remove the noise, and you can have this clean signal. So you can design a filter by going to frequency domain, that means. Another very important is advantage of the Fourier theory is it is useful to solve differential equations. For example, if you remember in chapter 2, how we can solve a differential equation, we have to have the homogeneous solution, the particular solution, and the complete solution. So it is a little tedious to do that. For example, in using Fourier theory, you can change this second derivative will become j omega squared times y j omega. Basically, you change the differential equation from time domain to frequency domain, and you can easily solve the roots of, for example, this equation, and after getting y j omega, you can change it to time domain to get y of t. Y j omega means the signal y of t looking in the frequency domain. So this is another advantage of Fourier transform. Okay, eigenfunctions and their properties. What is an eigenfunction and an eigenvalue? Now, suppose I have a system, this is my system, and the input to this system is a certain signal, let's call it phi k of t. Then when I look the output, I get y of t is equal to lambda k times phi kt, where lambda k is a certain real constant. If I observe the input and the output, what changes I see? Okay, the output is similar to the input. The only difference is it's multiplied by a certain constant lambda k. Okay, if we have such relationships, then the signal phi k of t is called an eigenfunction for the system, and lambda k is called the eigenvalue of the system. Now, what is the importance of this eigenfunction and eigenvalue? If we have a linear time invariant system, then we can break the signal x of t into subcomponents, into components, where x of t will be the summation of the different eigenfunctions. You see, summation of ak phi kt means x of t is decomposed into many eigenfunctions. And then we can find the output for each eigenfunction, okay, by multiplying by the corresponding eigenvalue. And we can be able to get the output yt without doing convolution. That means in chapter 2, we did it using convolution, which is sometimes gets complex for some signals. So y of t will become summation of ak lambda k phi k of t. Now, for our study for LTI systems, phi k of t are exponential functions, complex exponential function, e to the power of st, where s is a complex number. So let's summarize here. I have a system, a linear time invariant system. Then I can decompose the signal x of t into summation of ak phi kt, then the output y of t with summation of ak lambda k times phi kt, where lambda k is the eigenvalue of the system. So what do we need to get the output here, y of t? We need to know the system, and from the system we can get the eigenvalue lambda k. Of course, we need to know the phi k's, the phi kts, and we need to know the corresponding ak's, because for different phi k, I have different ak's. That means I need to be able to know the components of x of t when I am decomposing it as a sum of the eigenfunctions. Now, let the complex exponential signals, as we said, they are eigenfunctions. Let's say I have an eigenfunction x of t e to the power of st, where s is a complex number. And this is my system h of t, y of t. Let's try to find the eigenvalue for this system. Okay, from the concept and the theory of chapter 2, y of t is x of t convolved with h of t, which is from minus infinity to infinity h tau xt minus tau d tau, which is equal to from minus infinity to infinity h tau. Now xt minus tau means e to the power of s. This t will change to t minus tau. Then I have e to the power of st plus minus s tau. So by using the rule of exponential function, that is e to the power of a plus b is equal to e to the power of a plus e to the power of b. Then I can split this into two. Then I can get e to the power of st and e to the power of minus s tau. And we take it out of the integration because it is a function of t and doesn't depend on tau. So finally, I have e to the power of st times the integration of from minus infinity h tau e to the power of s tau d tau. When we do the integration with respect to tau, the resulting value will be h of s, h as a function of s. Tau will be eliminated. The variable tau will be eliminated, and I will have h of s. We call h of s the system transfer function. We will study more in detail about this in chapter 5. We call the system transfer function. Okay, so how we get the system transfer function? It's just from minus infinity to infinity, h tau e to the power of s tau d tau. In fact, tau can be t, no problem. From minus infinity to infinity, ht e to the power of st dt. So we can change tau to t, all of them to t. Now the output y of t becomes h of s. Remember, h of s times e raised to st. So what do we observe? Here the input is e to the power of st, okay? E to the power of st. And it's coming out also e to the power of st. The only difference, we multiply e to the power of st by h of s, which means h of s is the eigenvalue of the system. So y of t is h of s times e raised to st. Then find where h of s is this one. Okay, so this is eigenvalue and eigenfunction concept for complex exponential eigenfunctions. So in general, if I can be able to decompose x of t, the signal, the continuous time signal x of t, as a summation of ak e raised to skt. Now these are the eigenfunctions. Okay, as I said, now the eigenfunctions are complex exponential functions. Then if I can decompose the input signal as a sum of complex exponential, of course, scaled by ak, then y of t is the summation of h of sk ak e raised to skt. For Fourier theory or Fourier analysis, S is a complex number. So S is equal to j omega. So Sk means k times jk times omega. So we will study this in more detail in this chapter also. Okay, let's have a simple example here, some simple examples. Let's have a delay system. Okay, this delay system, when I give the input x of t, I get y of t x of t minus 3. If I have input x of t e to the power of j to t, what will be the output? Y of t e to the power of j 2t minus 3, which is equal to e to the power of minus j6 times e to the power of j 2t. So this is the input and this is the output. If I compare the input and the output, the eigenvalue is e to the power of minus j6. Okay, this is direct simple example. However, if we follow the procedure to find the eigenvalue, okay, first what we should do, we should find h of s. This is a delay system. Delay system means the system impulse response, as you see from this, is Dirac t minus 3. Why? Because if the input is x of t and the system Dirac t minus 3, then x of t convolve with Dirac t minus 3. At the output, I will get y of t is equal to x of t minus 3. Okay, That's why it is a delay system. So let's calculate h of s. H of s is from minus infinity to infinity Dirac t minus 3 e to the power of s tau d tau. Or you can keep this tau to t, everything t. So when we do this, the second function e to the power of s tau, because I am multiplying the impulse function with another function e to the power of s minus tau, because the impulse is located at tau is equal to 3. At all other locations it is 0. So the product will be 0 except at tau is equal to 3. So at tau is equal to 3, the second function will be e to the power of 3s. So e to the power of 3s will be constant. Okay, then we can take it out of the integration, and the integration of the impulse will be 1. So finally, the result will be e to the power of minus 3s. So h of s is e to the power of minus 3s. Now, s is j2. S is j2. So h of j2 will be e to the power of minus j6 when I put j2 here. So this is the eigenvalue. So if I split cosine of 2t into, if I write it as a combination of the eigenfunctions, I have two eigenfunctions, half e raised to j2t and half e raised to minus j2t. Remember, this is a way to write this using Euler formula. So again, this means this one will be multiplied now by the eigenfunction. Okay, this is the eigenfunction multiplied by the eigenvalue, each one. The eigenvalue for this is e to the power of minus j6. The eigenvalue for this is e to the power of j6. And then I have this. And when I simplify it, I will get cosine of 2t minus 3. So the same result. Okay, the same result I got. So if I have another input, cos of 40 plus cos 70, of course, straightforward, I can get it using the delay. Because I have a delay system, it will be cos 40 minus 3, cos 70 minus 3. But if I follow the eigenfunction and eigenvalue steps, so first I write this cosine 40, cos 70. Okay, cosine 40 is half ej40 plus half ej minus 40. Cosine 70, half e raised to j70, half e raised to minus j70. And then the eigenvalue for the first one, this is for this eigenfunction, s is j4. So h of j4 is e to the power of minus j12. H of minus j4 at minus j4, e to the power of j12. And h of, remember, h of s is e raised to minus 3s. Okay, as we found it here. This is h of s, e raised to minus 3s. So we just substitute for s. Okay, so so in the first case j4, it will be e raised to minus j12. In the second case, minus j4, positive j12. And s is j7, e raised to minus j21. And this e raised to j21. Then combine these two, I have this. And combine these two, I have this. And when I combine this, I get this and this. So when I change it to cosine form, cosine for t minus 3, cosine 7t minus 3. So as you see, we can get the output using eigenvalue and eigenfunction concept. This example is a simple relay system, although we can be able to find the output directly with a very simple step, one step. But this is to show you how the concept of eigenfunction and eigenvalue can be extended to more complex linear time variant systems with more complex input signal, that means. Okay, So I have also in the additional class notes more clarification here. Same thing actually. E raised to s of t, h of t, then what's y of t? Y of t is, we do the convolution, y of t is h of s times e raised to st. That means if I have e raised to st to the system input, the output is y of t h of s e raised to st, where h of s is from minus infinity to infinity h tau e raised to s tau d tau, or just change tau to t. Everything will be t. So from minus infinity to infinity h of t e to the power of st dt. Okay, this is called Laplace transform, and we will study it in more detail in chapter 5. So if I have again any signal can be written as a sum of the eigenfunctions, then y of t will be sum of ak hsk e raised to skt, and for Fourier analysis sk is jk omega naught t. So x of t is ak summation of ak raised to jk omega naught t, and when it comes out of the system, summation of ak h jk omega naught e raised to jk omega naught t. What we need here, we need to get h jk omega naught, we need to get ak. So we'll come to this in more detail in the future lecture class. So again, this is the same example. If I have cos 2t and if I have the delay system, Dirac t minus 3. So we write cos 2t in as a sum of the eigenfunctions. So half times e raised to j2t. The eigenfunction is this one, and it's scaled by half. Then the output will be half h of the s is j2 e raised to j2t, and half e raised to minus j2t. The output will be half h of at minus j2 because s is minus j2, so e to the power of j2t. And if I combine these two, the two inputs, the two eigenfunctions, I will get the cosine 2t. And then I have to, because the system is linear time invariant, then the output should be the sum of these two. Then add these two, and first we need to get h at j2 and h at minus j2 from the h of s function. So h of s, as I said, h of s is Dirac t minus 3 e raised to minus st here. Then this is this value t is equal to 3, it will be e raised to minus 3s, and we take out of the integration this impulse. The integration of this impulse is 1, so e raised to minus 3s, substitute j2, h at j2 e raised to minus j6, h at minus j2 e raised to j6, and formulate the output as a sum of the two eigenvalue times eigenfunction multiplication result here product, and then simplify, you'll get cosine 2t minus 3. Okay, in general, of course, this example is simple. If I have a delay system h of t Dirac t minus t naught, then the output is x of t minus t naught. Okay, we can get it directly, the output, but this example, this specific example shows you how the eigen function and eigenvalue concept can be used to get the output for more complex linear time invariant systems. Okay, thank you for listening to the lecture about eigenvalue and eigenfunction. See you in the next lecture class.